All right, so welcome to the comfort zone. You're in the comfort zone this morning and you're in Tech Corner. So you're in Tech Corner this morning. I do hope that you're enjoying your day, right? We need to conclude some work on Tech Corner this morning. And remember the last topic that we were talking about CAN bus. And so we're in the tech corner this morning. We're going to continue to talk about CAN bus, also CAN data transfer process and message in structure. All right. Remember last week we were talking about the CAN bus with the CAN high and CAN low. Okay, and so you're in the comfort zone this morning, and we're in Tech Corner today. And so the topic is still we're dealing with CAN data transfer process and message structure. All right. So we're going to talk about a little bit of the CAN process, the whole CAN data transfer process and message structure. So those who are want to be familiar with it, now you can stream in, you can listen, take some notes, right, and you can have some information for yourself. So there are two architectures that can be used in the physical CAN bus network. There are two, right? And we have been using high-speed CAN networks in all of our examples. So in the examples, we were using the high-speed CAN networks, right? And let us discuss it with the low, which is CAN low, and CAN high. And let us get into the standards. So let us talk about low speed CAN. The low speed CAN, right? The low speed CAN means that it's slow, specified by ISO. It's 11898-3. All right. So if you're taking notes, right, the low speed CAN is specified by ISO 11898-3. I'll go that again, 11898-3, and speed up to 125 kilobytes per second, right, over a maximum distance of 500 meters. All right. Low speed CAN is very fault tolerant, right? Low speed CAN is very fault tolerant. Okay. Um, so each device on the network must handle termination. And that we're talking about termination, we're talking about connecting of the resistors. Remember last week we mentioned, right? There is two terminated resistors at each end, and those resistors is their values are 120 ohms each, right? And because they're across the lines, right? At each end, they are in parallel. And just for simplicity's sake, right, because there are similar resistors and there's two resistors in parallel, we would say that because of the two, we will divide 120 by 2. And so the value of the resistor, the value of the measured value, so to speak, would be 60 ohms, because we're saying that 120 divided by 2 would give us 60 ohms. All right, that's it. So let us talk about the high speed CAN. High speed CAN, right? The high speed CAN is specified by ISO, and that is 11898-2. So this is specified by ISO. This is the high speed CAN, right? Which is the fastest at communication, the high speed CAN, right? Is specified by ISO 11898-2. So you had the low speed CAN, which is specified by ISO, which is 11898-3, and the high speed is dash 2. All right, same number, but they have the difference. One is dash 3, one is dash 2. So the high one is dash 2, and the low is dash 3. Remember that. All right, all those who are doing examinations, you might have a test or so forth. Remember. All right, speed of up to memory dealing here now with the high speed can speed of up to 1 megabytes per second, right, over a maximum distance of 40 meters. So the low one was had it had a maximum distance of 500 meters. The high will have a maximum distance of 40 meters. High speed CAN is very common in new vehicles. So you will see them in a lot of new vehicles, right? So a high speed CAN will is more common in new vehicles. And the CAN bus cable is terminated at both ends, as we mentioned, with the 120 ohm resistors. The nodes or the ECM do not handle termination. Remember, we were talking about nodes and we were identifying the ECMs. The ECMs, we denote them as, or we will explain that later, as nodes, or we just say ECM for short, which is the electronic control module or electronic control unit. Everybody, they have their different way that they will uh, describe these electronic modules. So the CAN bus cable is terminated at both ends. And remember that the ECM, right, the ECMs, right, do not handle terminations. That's why they're on the outside. They don't have the termination on the inside of the ECMs. All right. So let us get down to the CAN bus data message structure. So this is just some of information that we dealt with the practical aspect of it, troubleshooting, how to test it last week, right? We'll deal with some of the theoretical aspect of it today, right? Remember, I mentioned that we must be balanced with our with our the way we troubleshoot and the way we must have knowledge of what we're doing. We must have knowledge on how to troubleshoot. Our approaches to the way we troubleshoot will determine the knowledge that we have um, in this procedure. All right, so CAN bus data message structure. Let us go through that. The CAN system is further divided into two messages frame formats. And those formats are the 2.0A and 2.0B, right? Right? The two standards differed in size of the identifier ID, right? So I want to mention that again, and remember that you're in the tech corner. This tech corner is it's roughly 30 minutes. I don't want to take longer in the sessions per week. Remember that tech corner is once a week, and on a Saturday. Okay, so you in the tech corner. All right, you in the tech corner. You're in the tech corner this morning. You're in the tech corner. All right, so I do hope that you had a great week. Okay, great week, great week, great week. Okay, and so yeah, so we're back again. I remember I'm giving you a cue, right, on what we okay. So we were talking about the CAN system is further divided into two message frame, right? So there's two message frame, and the two message frame formats, right? There are two message frame formats, and there are 2.0A and 2.0B. The two standards differ in size of the identifiers, and the identifiers, those are the IDs, as we would call for short, right? Standard CAN, the standard CAN is version 2.0A, uses 11 bits identifiers in the arbitration field, right? So standard CAN, right? That is the version 2.0A, uses 11-bit identifiers in the arbitration field, right? And you might ask why call it a message frame, right? And you can think about a frame as a container or a fixed size that holds all of the pieces of a single message, your container that has everything just inside of it. All right. The extended CAN, so we spoke about that, we talked just now about the standard CAN, right, which is 2.0, the version 2.0A, and the extended CAN would be version 2.0B, right? So extended CAN, which is version 2.0B, supports a length of 29 bits for the identifier, made up of the 11-bit identifier, which is a base identifier, right, and an 18-bit extension. So we're talking about here the extended CAN version 2.0 supports a length of 29 bits for the identifier, and it's made up of the 11-bit identifier, which is the base identifier, and an 11 and sorry, an 18 bit extension. All right. So the basic structure of the message is the same for both standard and extension versions. And we can build a block, right? We can build a block. I'm probably gonna show you next week on the blog, but we're just going through the standard this morning, which is the CAN bus message frame structure, right? So on the canned bus message frame structure, right, you will have like for example the start frame, which is 1 bit, right? The start field, right? The start field, which is 1 bit. So you're looking at each ECM, and the start field, when they're sending message, you might send out a 1, right? And so and then we have the standard CAN version, which is the 2.0 A, which is 11 bits. All right, that is 11 bits. And then you have a message identifier, right, which we're going to go through that block. And then we have the extended CAN version, which is 2.0 B, which is 29 bits. And then we will get the control, which is 6 bits, and then we get data, which is up to 64 bits. All right. Also, we'll get the cyclic redundancy check, which is 16 bits, right? And a knowledge field we have, which is 2 bits, okay, on the knowledge field, which is come down to 2 bits, and the end field, which we have 7 bits. All right. So that is a little bit of for the CAN bus message frame structure, right? And then uh, we have the start field. Let us discuss the start field. So the start field, right? We were talking about the start field is 1 bit. The start field is identical in each and every message frame, right? It is a single dominant bit. Remember that we mentioned last week, we spoke about dominant bit on the pulse. And so we're talking, I mentioned here, bring it back to you again. 1 bit is always the dominant bit. And so it's a single dominant bit, right? Meant to inform the rest of the network that a message is beginning. So when a message is beginning on the CAN bus, right? The ECM sends a 1, right? The message is begin, right? So this is the start field. So in the start field, we have a start field of 1 bit, right? That 1 bit is the dominant bit, meant to inform the rest of the network that a message is beginning. So an ECM can start a message, right? And it will send this 1 bit out onto the bus, and the others would identify when this ECM is sending out a message, right? And then the message identifier, which is what we're going to talk about, because as the ECM send out this dominant bit, which is the 1 bit, right? They have the message identifier, which is the standard conversion, which is the 2.0A, which is 11-bit, right? So the next 11 to 29 bits are the message identifier. Whatever message the ECM is sending out, remember, this transceiver in the ECM is sending out these messages, right? It's getting the information down from the microcontroller and coming down to the controller, then to the transceiver, and the transceiver would send out the message onto the CAN bus, right? So the next 11 to 29 bits are message identifier, right? Right? These bits determine which message frame takes priority on the network if 2 frames begin transmitting at exact the same time. So let us get into that. So after the start field, which is the dominant bit, which is 1 bit, right? Then we go to the 11th to 29 bits. 11 and 29 bits, which we're talking about here, is the message identifier after the 1 bit or the dominant bit, right? So we're talking about the message identifier. And the message identifier is 11 to 29 bits, and the message identifier, right? The 11 to 29 bits are message identifier. These bits determine which message frame takes priority on the network if 2 frames begin transmitting at the exactly the same time. So if you have 2 ECMs, right, and they're transmitting at the same time, right? So these 2 ECMs are transmitting ones and zeros, right? And so we will get into that because it's these bits determine which message frame takes priority on the network. If 2 frames begin transmitting at exactly the same time. So you might have two ECMs that want to send out message at the same time, but one have to take priority. All right, and the message identifier would determine which one would take the priority, which one would becomes the first to send message on the data link, providing that you have we can be looking. Let us look at four of the ECMs. We have four ECMs, right? And you have two that is at the same time setting up. Okay. And then we have the control. That the control is as known as the check, right? So the control field, which is known as the check, is the control field. This field displays the number of items of the information contained in the data field. So this field, which is the control field, right, it displays the number of items of information contained in the data field. This field allows each receiving node or each ECM to determine whether it has received all the information transferred, right? So the field allows this control field, right, allows each receiving ECM or node to determine whether it has received all the information transferred, right? Then we have the data field. The data field, right, this is the actual data to be transferred. It can be up to 64 bits, but it doesn't have to be, okay? The exact length of the data field is specified in the preceding control field. So it doesn't has to be the full 64. All right. Then we have the cyclic redundancy check field, which is the safety field. Right. All this thing is happening on the system. Right. So you have to know some of the process, which is very important. This field summarizes the values of the info in the data. So the cyclic redundancy check field, which is a safety field, right? Right? It's summarizes the value of the information in the data field. This is known as the checksum. And sometimes you will, I sure you're working with electronics or some of the microchips, and you will hear about this term checksum. If there is mismatch between that value and the value uh, of the data field received by the ECM or by the node, there must be an error. I want to go through that again carefully, right? This field summarizes, which is the cyclic redundancy field, which is we known as the safety field, and it also known as the checksum, right? It summarizes the value of info in the data field. If there is a mismatch between that value and the value of the data field received by the ECM or the node, there must be an error. All right. And then we have the acknowledge field, which is the confirmation field. The confirmation field, right? When it reaches the acknowledge field, the transmitting ECM or the node sends a recessive bit. So when it's acknowledged to send, right, then it would send it. The transmitting ECM, or the transmitting node, sends a recessive bit. And you know, what is the recessive bit? So this recessive bit, when we were discussing dominant bit, right? Uh, and recessive bit. We spoke about that. And if you have your notes, right, we were talking about recessive and we were talking about dominant. So we were talking about dominant, which is a zero, right? And a recessive, which is a one, right? The dominant, so when when it's ready for transmission, the ECM is transmitting now, it sends a recessive bit, but monitors the bus for a dominant bit, right? It monitors the bus for a dominant bit. This is the moment for the receiving ECM or the node to signal that they have received a syntactically right correct CAN bus message frame, right? By overwriting the recessive level on the bus with a dominant bit. I want to read this thing before, I don't want you to get confused. So we in the acknowledge field. So in the acknowledge field, when it reaches the acknowledge field, right? The transmitting ECM sends a recessive bit, but monitors the bus for a dominant bit. Dominant bit is zero, as we would know it as 0 bit, right? And recessive, we know it as 1 bit, right? So let us continue that. But monitors the bus for a dominant bit. This is the moment for the receiving ECM or the node to signal that they have received a syntactically correct CAN bus message frame. So it gets a correct message. So it acknowledges it by overwriting the recessive level on the bus with a dominant bit. So it is sent out back. Okay? And so on the end field, right? This field marks the end of the message frame, right? From whoever ECM was the dominant one, right? That sends a message. The end field is always the same in every message frame. 7 recessive bits. If a dominant bit is seen on the bus during the end field, it is signal that there is an error because you're not supposed to see that, right? So sample messages, sample message frames. We want to go through that and then we want to close off because we already 30 minutes. I want to just go through the sample message frame. There could be a lot of data in a message frame, as much as 125 bits if the data field uses all 64 bits and you are using CAN 2.0b or 2.0b, which is the extension, right? There could be a lot of data in a message frame, as much as 125 bits, right? If the data field uses all 64 bits and you are using CAN 2.0b. All right, so all 125 bits, right, will show up on your it will show here on your CAN data bus, right? It is are just a single message frame. It will show up, okay? And so that 120, we were talking about 01001101. So we were talking about that. 0 1 0 0 1101. That this is your message, the sampling, right? It's going to be sampling. I'm going again on the data bus with your network and the pulse, right? You remember your pulse, right? On the what we call the can high is 0 bit. Recessive bit is on the 2.5 that we mentioned last week, right? On the bus. I'm not showing it here right now, but I want you to have that in your head, right? To understand. And then you have two zeros. With two zeros is the dominant bit, which is on the can high. So you have the 40, which is a dominant bit on can high. Then you have also you have at the inverted part, right? Remember, it would be a differential, right? You have a dominant bit as well. And then on the recessive, right, which is 1 bit, right? And remember on that recessive line, we had it as 2.5. And so we have on the dominant bit, which is the upper and the inverted, right? We had a differential, and that differential was 2.5, right? And so you remember the message sampling we're talking about here today is 0 1 0 0 1 1 0 1. All right. Don't forget that the CAN bus network is capable of transmitting up to a 1 megabyte per second. That means that a top speed, the network could transmit almost, right? Almost 64,000 of these 125-bit messages within a single second. So almost that means that a top speed, the network could transmit almost 64,000 of these 125-bit messages within a single second. All right. So you were in the comfort zone, and you're connected to Tech Corner, and I do hope that you enjoy, because we still have to come back to finish off the CAN bus protocol, right? We're gonna go through CAN bus protocol, and we're gonna go through also the clear communication, what is taking place on each ECM as they send out data on the CAN bus, who are going to accept, who going to acknowledge that we're going to receive it, or they reject it. Okay. And so I do hope that you enjoy it, because next week we will talk about also the message arbitration, right? And you would see how what happens with the message ID from one ECM to the next ECM, and then we will go through some review. Okay, so I do hope so. Today we were discussing here. This is just the CAN data transfer process and message structure. Okay, I do hope that you can take notes, and you can you know put all of these things in your troubleshooting knowledge, and your program. And so remember that a little bit of recap, we spoke about low speed CAN, high speed CAN bus data message structure, right? We mentioned, we spoke, we talk a little bit about CAN bus message frame structure, the start field, the message identifier, the control field, which is known as the checksum or the check, right? We spoke about the data field, the cyclic redundancy field, which is the safety field, and the acknowledge, which is the confirmation field. All right. And then also we spoke about the Enfield. So, and then I give you some of the sampling, which we mentioned the message, right? 01001101, and that is the binary, and that is the message, okay? And so you were in the comfort zone, and we were talking about uh this candidate process. All right, so you in the you were in the podcast, and remember the podcast comes to you every week on Saturdays, and you can enjoy. You can have that. Okay. All right. So I do hope you enjoy the rest of the day, and God bless you.